Okay, so this is the second part of inverse functions, a lesson dealing with inverse functions. Remember from part one that an inverse function is a function that will undo anything that an original function does. All right, and so one of our examples in part one was this function here, this linear function, 2x minus 5. So we saw that for any value of x that we substitute into the function, this function multiplies it by 2 and then subtracts 5. So to undo this operation, this function, to find its inverse, we have to do the opposite. So if this function uses the operations multiplication and subtraction, then the inverse function will involve the operations addition and division. And in fact, we saw that the inverse function for f of x equals 2x minus 5, and let me see, I can use this one instead, so they'll be side by side. So the inverse function of f of x is, remember, is g of x, so we got x plus 5 divided by 2. All right, now in part 2, we're going to come back and look at these two tables for a continuation of a discussion dealing with inverse functions. Now, one of the questions we asked at the end of part 1 was this. So this was the final question that we asked. Do all functions have an inverse? And so that's going to be part of what we're going to discuss in part 2. So do all functions have an inverse? That's the question that we need to work on. Okay, first of all, let's remember something about functions. So remember, a function is defined as a relation in which for each x coordinate, there's exactly one y coordinate. And so that should be singular right here. So for each x, there's exactly one y. So, for example, this function here, which is defined to be quadratic, f of x equals x squared minus 4, this is a function. Well, first of all, we defined it using function notation, so you know it's a function, but remember why it's a function. So if I look at any of these x values here, when x is negative 3, there's only one y value. When x is negative 3, the y value is 4. There's no other y value. When x is, let's say, 0, there's only one y value, negative 4. There is no other y value. When x is 3, there's only one y value, it's 5. All right, and recall also that we use the vertical line test. So if you use the vertical line test, I'm going to just call it VLT. Vertical line test, remember it passes vertical line test. No matter where I draw this vertical line, it intersects the graph once, which means that for each x coordinate, whatever these x coordinates are, there's only going to be one point on the graph, so there's only going to be one y value. So the same thing here. So g of x is a function because for each x value, notice when x is negative 4, there's only one y value, whatever that y value is. So when x is negative 4, my y value is 1. I didn't do a very good job drawing this, but my y value is 1. When x is negative 1, there's only one y value. The vertical line test, see, it only intersects it here. There's only one y value. That y value is 2. So no matter where I draw that vertical line, the vertical line test, this relation is a function because there's only one y value at each of those x values. So again, if I look at the horizontal line, if I look at this horizontal line, notice that for each x value, there's only one y value. And it doesn't matter that all these y values are the same. It's just that for each x, when x is negative 7, does it follow the definition of the function? For each x value, there has to be one y value, and there is. When x is negative 7, my y value is 4. When x is negative 6, my y value is 4. When x is negative 5, my y value is 4, and so on. So this is a function. We also discussed, when we looked at functions in an earlier lesson, we discussed ordered pairs. So remember, with an ordered pair, remember the definition of the function. For each x value, there's only one y value. So we used a mapping in this case. So from x to y. Because remember, for each x, there's got to be one y. That was the definition of function. So if I look at the mapping in terms of x to y, if I look at it in terms of x to y, when x is 2, there's only one y value. It's 4. When x is 7, my y value is negative 1. When x is 3, my y value is negative 2. When x is 6, my y value is 5. So notice that for each x value, there's only one y value. So this was a function. So this is a function. Over here, I'll look at this one, same thing. If I look at this in terms of a mapping from x to y, because that's the definition of the function for each x, there's got to be one y. So look at your x's and see what my y values are. So if x is 0, my y value is negative 2. So far, I'm good. When x is 5, my y value is 1. So far, I'm good. When x is 6, my y value is 3. So far, I'm good. When x is 2, my y value is negative 7. When x is 4, my y value is negative 2. Now, don't list it again because it's already listed. So just draw a line going here. Okay? So notice that for each of those x values, my y value, there's only one y value. Now, remember, for this, it's okay for a function, for function, it's okay for different x values to have the same y value. Okay? So that's so these are functions. Now, here's the situation. 1, 2, 3, 4, 5. So we looked at 5 functions here. These are all functions, obviously, but not all of these functions have an inverse. Not all of these functions have an inverse. Some have an inverse, some do not. So that's what we have to discuss. How can we tell if a function has an inverse? Okay, so that's the next part that we need to discuss. All right, so obviously we now know that not all functions have an inverse. So it's important to determine whether or not a function has an inverse before we try to find it. If a function does not have an inverse, then we need to realize the function does not have an inverse so we don't waste our time trying to find something that does not exist. So how do we know if a function has an inverse? To determine if a function has an inverse, we need to discuss a special type of function called a one-to-one function. All right, so a one-to-one function. So we know what a function is. We know the definition of function. We know the definition of function. For each x value, there's got to be one y value. Now let's discuss what it means for a function to be one-to-one. So if a function is one-to-one, then it has an inverse. All right, so here we go. A function, a one-to-one function is defined as this. A one-to-one function is a function. So first of all, it has to be a function. So hence in the term is one-to-one, and then you see the word function. So it has to be a function. So this has to apply. For each x coordinate, there's got to be exactly one y coordinate. All right, if that doesn't apply, then it's not a one-to-one function because it's not a function to begin with. It first of all has to be a function. All right. But in order for that function to be one-to-one, each x value has a unique y value. Notice I'm using the word unique. There's only one y value that's going to apply to it. And that y value cannot be used again. Hence the word unique. Each y value has a unique y value. In other words, every time we plug in a value of x, we will get a unique value of y. In other words, the same y value will never appear more than once. The same y value will never appear more than once. So a one-to-one function, for each x value, there's only one y value, and that y value cannot appear again. So let's look at the definition of function. Definition of function. For each x coordinate, there's exactly one y coordinate. Okay? And we saw that in a function, different x coordinates can have the same y coordinate. All right, and that was okay for definition of a function, for it to be a function. But a one-to-one function, in order for it to be a one-to-one function, the y value can never appear more than once. So each x value, there's got to be a unique y value, and once that y value is used, it cannot be used again. So in other words, a one-to-one function is defined as a function in which for each y coordinate there is exactly one x coordinate. So see the definition of function. So remember in the previous lesson we said that a inverse function undoes what a function does. So we said that for the x becomes y and the y becomes x. So notice that for each x coordinate there's exactly one y coordinate. So reverse it. For each y coordinate, right here, for each y coordinate, there's exactly one x coordinate. So just think of the inverse. For each y coordinate, there's exactly one x coordinate. Okay? All right, so a one-to-one function is special because only one-to-one functions have an inverse. So in order for a function to have an inverse, it's got to be one-to-one. All right, so remember a function, for each x coordinate, there's exactly one y coordinate. A one-to-one function, for each y coordinate, there's got to be only one x coordinate. There's got to be only one x coordinate. And then if this is a one-to-one function, then we can find the inverse. Okay, now let's go back and look at this example right here. Okay, so we know it's a function because it passes a vertical line test. All right, now what I want to do is this. I want to look at some ordered pairs here. And so I'm going to list some ordered pairs. I'm going to list some ordered pairs that's on this graph. So for example, 3, 5 is on this graph. So 3, 5 is, 3, 5. 3, 5 is a solution. So when I substitute 3 squared is 9, 9 minus 4 is 5. All right, and so is the coordinate, so is the point, -3, 5. Over here, I have, right here, let's just do this one. I have 1, -3, and I also have -1, -3. Now, just looking at the first one, I have this now. Okay, so I'm going to look at this mapping. From x to y, just to show you that this is a function. When x is 3, I get a y value of 5. And when x is -3, I get a y value of 5. When x is 1, I get a y value of -3. And when x is -1, I get a y value of -3 as well. So that's still a function. For each x, there's only one y value. Now let's talk about the inverse. Okay, let's talk about, is there an inverse? Now remember, if in order for there to be an inverse, it's got to be a one-to-one function, meaning that for each y, there's got to be one x. So notice that for a function, I started with x, look to see what y value is. To determine if it's one-to-one, I started y and then looked at my x value. Okay? All right, so let's go back over here and start with y. So when y is 5, I have an x value 3. When y is 5, I also have an x value of -3. So right away, I can tell that this is not a one-to-one function because it fails the definition of one-to-one function. Remember, one-to-one function says that For each y coordinate, there's exactly one x coordinate. You're going to have just one x coordinate. All right, so this is not a one-to-one function. Now, remember when we talked about a function and we used the vertical line test? So for each x value, there was only one y value. So all these were functions. But now we know that this is not a one-to-one function. So we know that this is not a one-to-one function. So there is a test that you can use to determine if a graph of a function is one-to-one. So to determine if it's a function, we use the vertical line test. To determine if this graph of a function is one-to-one, we can use the horizontal line test. Horizontal line test. And the horizontal line test will help to determine if a function is one-to-one. I'm going to write it like this, one-to-one. All right, so notice, just like a vertical line test, when I draw the vertical line, it can only intersect it once. Only intersected once. Which means that for each of these x values, there's only one y value. When I do the vertical line test, the horizontal line test, let's go back in this one right here. Notice, no matter where I draw this horizontal line, for each of these y values, see this y value right here, when y is 5, there are 2 points in the graph, meaning there are two different x-intercepts. Two different x values. I didn't mean the word intercept. Two different x values. Here, when x is 3, there are two different y, when y is 3, good Lord, when y is 3, there are two different x values. When y is 1, there are two different x values, and so on. So when y was 5, there were two different x values, namely 3, -3. So it fails the horizontal line test. So since it fails the horizontal line test, I'm going to call it HLT, horizontal line test, then f of x is not one-to-one, so there is no inverse. All right, so there is no inverse. Okay, so now let's look at this one right here. And all I want you to tell me is this function one-to-one? If it's one-to-one function, then it has an inverse, and you can find it. Okay, so notice first of all, it passes the horizontal line test. You see, when I draw a horizontal line, notice that when y is 1, there's only one x value. When y is 2, there's only one x value. When y is 3, there's only one x value, and that x value here is 4. When y is 4, there's only one x value, that's 11. So notice that this has an inverse. This has an inverse because it passes the horizontal line test. So since it passes the horizontal line test, g of x is a one-to-one function, and it has an inverse. All right. Even if you did not have the graph, see, I drew the graph for you, but even if you did not know what the graph looked like, you could use a t-table to help you determine whether it's one-to-one. All right, so for example, if x is 0, a y value is the square root of 5. There is no other y value for 0. If x is, let's say, 1, y value is square root of 6. If x is, now notice I cannot use -6, for example. I cannot use -6 because then I would have the square root of a -1, and that's no longer a real number. So in some cases, notice that the domain here, the domain of the graph, is from -5 to infinity, whereas the domain here is all real numbers. All right, so here I really need to say, in case of my domain would be any real number greater than or equal to -5. So those are only x values I can use. So when x is, let's say, -5, I get the square root of -5 plus 5 is 0. I get the square root of 0, which is 0. When x is, let's say, 11, I get the square root of 16. 11 plus 5 is 16, which is 4. But the point being this, notice that no matter what number I choose for x, there is a unique y value. See, that y value doesn't appear anywhere else. Square root of 5 is not appearing anywhere else. Square root of 6 does not appear anywhere else. 0 does not appear anywhere else. That was a, what was that? That was a 4. 4 does not appear anywhere else. All right, and you keep on going, you can see that's going to be the case. All right, so this is one-to-one function, so therefore it has an inverse. Okay, now, before we look at this one, remember we said those were functions. Before we look at this one, I want to go back to part 1 of our lesson, and I want to look at these two functions. Remember, we said these two functions were inverses. Those were inverses. Okay? And so I want to do this. I want to rewrite some ordered pairs for this function here. All right, so let me go back and kind of do it here. So for f of x equal 2x minus 5, remember there are an infinite number of points on this graph. All right, but we just looked at 5 of them here. So I'm going to go ahead and list those 5. So these ordered pairs are on this graph. So we have the ordered pair 2, -1. We have the ordered pair 4, 3. We have the ordered pair 0, -5. We have the ordered pair -1, -7. And we have the ordered pair -2, -9. Okay? For the inverse, now we now remember the notation. We looked at notation. So instead of using g of x, now I'm going to use f inverse of x. So remember, this -1 does not mean an exponent. That means f inverse of x. That's how you read it, f inverse of x. So the inverse of f is this. So here's some ordered pairs that's on the inverse. So the inverse, remember, -1, 2, 3, 4, -5, 0, -7, -1, -9, -2. All right, so those are some ordered pairs that's on f of x, and the ordered pairs, some ordered pairs that are on the inverse. Now, when we did part 1, we noticed this. We noticed that the on f of x, if the point 2, -1 is on the graph of f of x, then the point -1, 2 is on the graph of the inverse. So basically, remember we said x becomes y, y becomes x. And remember we looked at the line of symmetry y equal x, and that's how we also discussed the line of symmetry in part 1. See that blue line right here to the line of symmetry? All right, so that's where all this comes about. So here's what I want you to notice. If you're given a set of ordered pairs, see these are ordered pairs. The inverse, you just change the x and the y's. So x becomes y, y becomes x. X becomes y, y becomes x. X becomes y, y becomes x, and so on. All right. Now, first of all, though, you got to make sure that this function is one-to-one, and it is. We saw that it is. Notice that for each of these y coordinates right here, there's only going to be one x coordinate. When x is -1, The only x-coordinate when y is -1, the only x-coordinate you can get is 2. When y is 3, the only x-coordinate you can get is 4. There's going to be no other x-coordinate for when y is 3. So this is going to be 1 to 1, and you can find the inverse. And so to find the inverse, you just reverse the coordinates. Okay, now let's go back and look at this now. All right, so right here. So we saw that these are functions. Now, first of all, let's determine if it has an inverse. All right, so number one, let's determine if number one has an inverse. So if it has an inverse, let's look at the mapping, y to x. So remember that it has to be 1 to 1. So in order for it to be 1 to 1, for each y coordinate, there's got to be only one x coordinate. Okay? A function is the other way around. For each x coordinate, there's got to be only one y coordinate. All right, so when y is 4, my x value is 2. When y is -1, my x value is 7. When y is -2, my x value is 3. When y is 5, my x value is 6. So this ordered pair, which I'm defined, which has the name f, this ordered pair is 1 to 1. So since f is a 1 to 1 function, it has an inverse. All right, so since f is a 1 to 1 function, it has an inverse. So let's find it. So we're going to call it f inverse just like this. That's all you do. Just say f inverse. And so the ordered pair, let's see, 1, 2, 3, 4. There are 4 ordered pairs here. It's going to be 4 ordered pairs here. So how do you find the inverse? Well, remember we did. The x becomes y, the y becomes x. X becomes y, y becomes x, and so on. So if the point 24 is on the function f, then for 2 is going to be the inverse. If the point 7, -1 is on the function f, then -1, 7 is going to be the inverse. If the point 3, -2 is on the function f, then -2, 3 is going to be the inverse. If the point 6, 5 is on the function f, then 5, 6 is going to be on the inverse. And so there's your inverse. So that's how you find the inverse of a set of ordered pairs, if it's 1 to 1. Okay, number 2, let's look at number 2. Notice number 2 is a function. We talked about that earlier. Now let's see if it's 1 to 1. Is this a 1 to 1 function? All right, so for each, we're going to look at the y values and see what the x values are. So when y is -2, I get an x value of 0. When y is 1, I get an x value of 5. When y is 3, I get an x value of 6. When y is -7, I get an x value of 2. When y is -2, now I already have it, so don't listen again. When y is -2, I get an x value of 4. And right away, you know that this is not 1 to 1. So g is not a 1 to 1 function. So 1-1, 1 to 1, is not a 1 to 1 function. So therefore, g does not have an inverse. Okay, so g does not have an inverse. All right, so remember, for each y coordinate, you can only have one x coordinate. So when y is -2, there are 2 of them. So it's not 1 to 1, so it doesn't have an inverse. All right, now let's, in the previous lesson, when we did the previous lesson, we looked at inverses. We looked at functions that were linear. Remember that? These were linear. So all these functions that we looked at, f of x equals 2x minus 5, g of the inverse, x plus 5 divided by 2. We looked at g of x equals 3x plus 2. The inverse, x minus 2 divided by 3. So they're linear. So we saw that those were one-to-one functions. In fact, if you drew a horizontal line, you would see that it would intersect the red graph and the purple graph only once. Okay? So any linear function, so you may think, well, are all linear functions one-to-one functions? No. Only linear functions in which the slope is not 0. Only linear functions in which the slope is not 0. So the slope is not 0, then it's a one-to-one function. All right, so now that I said that, let's discuss what I just said. Y is a linear function. Y is a linear function that has slope 0, not a one-to-one function. So y is a linear function that has slope 0, not a one-to-one function. Okay, so let's discuss that. So suppose we have this linear function y equal 4, all right, or f of x equal 4. Remember, that's the same thing as saying y equal 4. So there's the graph, and we already saw that it was a function. And remember, it is a horizontal line, so we know that the slope of a horizontal line is 0. So the slope is 0. So this linear function, remember, y equal a number, has slope 0. It's a horizontal line. So all horizontal lines, no matter what my horizontal line is, the slope is going to be 0. So it turns out that if your linear function has a slope 0, it is not a one-to-one function. Okay, so let's look at why. So if I look at all these points here, so if I look at the ordered pair, -7 for, -6 for, -3 for, let me do that here, -3 4, and so on, and I look at whether it's one-to-one. So is this function one-to-one? One-to-one. Is this function one-to-one? Well, let's look at the mapping. Y, x. So when y is 4, my y value is -7. Now here's the problem. When y is 4, I also get a y value of -6. And in fact, I get a y value of 4. In fact, I got an infinite number of y values. I'm sorry, I didn't mean y value, I mean x value. When y is 4, let me do this again. When y is 4, I get an x value of -7. When y is 4, I get an x value of -6. When y is 4, I get an x value of 4. In fact, I get an infinite number of x values. So it fails the horizontal line test. So because remember, when I draw the horizontal line, it intersects this linear function more than one place. In fact, an infinite number of places. Okay? So any linear function except those that are horizontal will have a one-to-one function and will have an inverse. Okay? All right, so that will take care of part 2 of this lesson. And what we're going to do next in part 3, here's what we're going to do in part 3. So in part 3, we're going to determine algebraically the inverse of a function. Okay, so determine algebraically the inverse of a function. So that's going to be the part 3 of the continuation of inverse functions.